Good morning, ladies and gentlemen. Welcome to Forum 3 of Medical Korea 2024, which is themed Korea's Pioneering Initiative for Overcoming Severe Diseases. Allow me to introduce myself. My name is Sowa Kwon, and I'm your MC for today's forum. Thank you very much. It's my absolute honor and privilege to be here with you tonight for this morning, of course, and for this significant and meaningful event, which I hope is going to be fruitful for everyone here participating. So first and foremost, I would like to thank all our distinguished guests and participants for taking time out of your busy schedules to attend this forum. Now, before we kick off with the presentations, I would like to kindly remind you that we provide simultaneous interpretation in both Korean and English. So please use the interpretation receivers that we handed out to you as you entered the venue. So once more, channel 1 is for Korean and channel 2 is for English. 네, 본격적인 시작에 앞서 여러분 리시버 채널을 잘 맞춰주셨는지 확인
Ladies and gentlemen,
부탁드리겠습니다.
please tune to channel number 1 for
1번입니다.
Korean, channel number 2 for
And if you need
English.
any assistance, please reach out to
오늘
our
행사
staff
도중
here
도움이
on
필요하신
standby at
분들께서는
the venue.
행사장 내에 운영
Medical
스태프에게
Korea
알려주시기
now is
바랍니다.
in its 14th
올해
iteration, offering
14회차를
various
맞은
programs both online and offline over the next 2 days. And by searching Medical Korea 2024 Forum 3 on YouTube, you can watch the live stream of this forum and actively participate in the live discussions. And we appreciate your interest and encourage your active participation. And now, without further ado, we will commence Forum 3, Korea's Pioneering Initiative for Overcoming Severe Diseases. And I would like to now introduce our distinguished guests who are here with us today. 네, 시작하기에 앞서 저희 내빈 소개를 잠시
Before we begin,
해드리도록
we are going to
하겠습니다.
introduce our
네,
distinguished
오늘
guests.
우선
First of all,
한국보건산업진흥원
we have President Sundo Cha of the Korea Health Industry Development Institute is here with us. Please welcome him with a big round of applause.
네, 그리고 또
We also have Cultural Attaché Al-Dayel from the Saudi Arabian Cultural Mission to Korea. Thank you very much. Now we have Professor Lee Seung-gyu from Seoul Asan Medical Center. Thank you so much. We have Professor and Director of Seoul National University Hospital. Thank you very much. We have Mr. Mitchell C. Posner, Vice President of Chicago Medical Center. Thank you very much. We have Professor Gi-jong, the Director of the Lymphoma Center at St. Mary's Hospital of the Catholic University. We have Hitcher Park, the Samsung Medical Center's Director of the Particle Therapy Center. We have Professor Ujin Hyung, Professor of Yonsei University College of Medicine. Thank you very much for attending this forum.
With us today. So now to kick off this event in full swing, we will invite congratulatory speakers. The first congratulatory remarks will be given by President Sundo Cha of the Korea Health Industry Development Institute. Please welcome him with a big round of applause.
Good morning, ladies and gentlemen. I am Sundo Cha, President of Korea Health Industry Development Institute. Marking the 14th anniversary of the Medical Korea 2024, I would like to thank everybody for attending this important event. I sincerely extend my appreciation to all of you for honoring this event with your presence. This event is really meaningful as it opens a platform for sharing the knowledge and insights with experts and participants around the world. And I would like to extend my special thanks to Professor Seung-Yu Lee from Asan Medical Center and Professor Kim Young-tae from Seoul National University Hospital and Mr. Mitchell Postner and Professor and also I would like to thank Professor Heecher Park from the Particle Therapy Center. And also I'd like to thank Professor Hyung from Yonsei University College of Medicine. All these distinguished guests are the witnesses of ever-developing medical technologies. Today, we are going to discuss the advanced technologies of treating severe diseases. And also, we are going to discuss the next generation therapies and medical technologies for the future. In treating severe diseases, we have made great progress based on advanced technologies. Korea's top 5 cancer patients' survival rates actually surpassed that of the United States. Severe diseases represented by cancers are the common concerns for all humanity, so we need to work together to overcome these severe diseases. So organ transplantation and particle therapies, in these areas, we will be able to hear the success cases and insights from renowned experts and specialists, and we will also have an opportunity to explore new opportunities in treating severe diseases. Once again, I'd like to thank our 6 prominent speakers and all other participants. I wish you success. Thank you very much.
Thank you very much, President Ta, for opening up the event with those warm remarks. And we hope that we do overcome the remaining tasks in dealing with severe diseases, as you mentioned. Let's give him another big hand. And the second congratulatory speech, ladies and gentlemen, will be delivered by Dr. Abdulaziz Abdurrahman Al-Dayel, the cultural attaché of the Saudi Arabian Cultural Mission to the Republic of Korea. Please welcome him with a big round of applause.
Good morning, everyone. Distinguished guests, honorable attendees. It's a great pleasure and honor, tremendous respect, and a lot of humbleness that I will be standing before you today, beginning this important scientific panel discussions on cancer treatment at Korea hospitals. This assembly here does not just mean our joint commitment in the fight against one of the most serious enemies in human health. It also serves as a powerful example of what an incredible stride we have taken in this endless fight. The strides and innovations observed in the medical and technical cancer treatment methods made available in Korea are commendable, laudable, to say the least. Some of the advancements developed here are amongst the best in the world. And by having them, it raises its reputations for being pioneering and committed to carrying out the best excellence in healthcare. It's with pride that one admires the hope from many around the world, including the footprints of my country, Saudi Arabia, for setting a new paradigm in the state-of-the-art treatment options, pioneering research and reaching a humanistic side of patient care at Korea hospitals. That then is combined by admiring this scientific role in the development of a treatment for cancer, realizing its immunity's importance, and not necessarily just for one nation, but for the whole of the humankind. This then stands testament to the kind of spirit these collaborations represent and shared knowledge that exceeds borders to unite us toward a common goal, saving lives and improving the quality of those living with cancers. My country is interested in the progress that is being made here, thus feeling of attention and realizations in them toward what potential can be drawn from an effective partnerships between our nations. We are interested in the opportunities and areas of collaborations at different levels: training, treatment, and treatment and scientific research. We will complete each other by bringing our collective skills together and pooling valuable insights and to build one each other in developing innovative solutions that will promise to light a bonfire for brighter futures for cancer patients across the globe. Such cooperations is not merely beneficial, but is essential. And solely in this complexity, it requires us to get invested in many approaches, those including the best of our scientific knowledge, the clinical and technological advancement. This way, great strides in treatment methodologies and patient care can be made, and ultimately toward the cure. Let's keep those huge responsibilities and much more scientific impact in today's conversations. With the road seeming hard, but with mutual support and joint vision, there is not one barrier that cannot be taken down. In conclusion, I want to humbly express my heartfelt appreciation for the opportunity to make these opening remarks of these very distinguished panel discussions. I am indeed privileged to be in such a valued meeting and look very much forward to the interchange of ideas, discussions, and the future partnership that are formed out of today's deliberations. Big thanks, and keep going with the good work you are doing with all your effort and dedications. Let us inspire each other further to build this world in such a way where the same kind of threat from cancer does not exist as it is today. Thank you very much for listening.
Thank you very much for your encouraging remarks, Dr. Al-Dayel, and also thank you for your attendance at Medical Korea 2024. We do also hope more cooperation between Saudi Arabia and South Korea in the medical field. Let's give him another big round of applause for those remarks. So thank you very much for those congratulatory words. We will now move forward with the presentation session featuring a total of 6 presentations. So I hope that this forum will be productive and informative, facilitating the exchange of valuable information. As for the first presentation, Dr. Young-tae Kim, President and CEO of Seoul National University Hospital and the President of the Korea International Medical Association, will present on current status of foreign patients with severe diseases and new opportunities for medical technological innovation. Dr. Kim is a world-renowned authority in lung cancer treatment and lung transplantation. He identified the fusion gene responsible for lung cancer for the first time in the world and holds the distinction of successfully performing the first lung transplantation surgery on a child under the age of 2 in Korea. So let's give him a big round of applause for the first presentation.
I'm going to conduct my presentation in Korean because the majority of the audience is Korean. As was just introduced, my name is Young-tae Kim. I'm the director of Seoul National University Hospital. I usually research lung cancer and conduct lung operation and surgery and lung transplantation. But today, I'm not going to talk about lung cancer, but as the president of Korea International Medical Association, I'm going to talk about how to attract foreign patients and also how to create new opportunities in healthcare. This is the table of contents of my presentation. First, I'm going to talk about the current status of medical tourism in Korea, and then I'm going to talk about the current healthcare service standards and status in Korea. Third, I'm going to talk about the major diseases or severe diseases. In English, the proper term, I believe, it is severe diseases. So I'm going to talk about medical cost for major or severe diseases. And I'm going to see the comparisons of Korea's current standing with the United States and other Asian countries. And against this backdrop, lastly, in my presentation, I'm going to talk about the strategies to expand medical tourism in Korea. First, current status of medical tourism in Korea. In 2009, there was a revision of medical law. So this law actually enabled us to take better care of inbound and outbound patients. So we were able to attract more foreign patients, and also many Korean hospitals advanced to overseas markets. So in Korea, the foreign patients increased 22.7%. It is attributed to many factors, and many different countries are sending their patients to Korea. And also, Korea's healthcare services has elevated. And we have presentations from Big 5 hospitals in Korea. So I believe we have a state-of-the-art medical technologies at Korean hospitals centering on major 5 hospitals. This is the number of foreign patients visiting Korea, but the number all of a sudden dropped. It was due to COVID-19 pandemic. So now it's picking up. So in 2022, we saw an upward trend in the number of foreign patients visiting Korea. I believe this trend will continue. From 2009 to 2022, the largest number of patients came from China, followed by the US and Japan. I see Americans in the audience. We have a representative from Chicago Medical Center. The Korean Americans living in America are actually attending and participating in this forum. I was also trained in America, and I'm aware that the medical accessibility in America is really low, and there's also communication issues for Korean Americans living in America. As of 2022, the largest number of patients came from the United States. The China did not catch up yet due to political issues, because China did not lift the quarantine for COVID-19 in 2022. But given the past data, I believe there will be more patients visiting Korea from China and other Asian countries. About 35% of patients received care at academic medical centers. Korean medical services are well known for plastic surgery and dermatology, so you might think there'll be a lot of foreign patients receiving such medical services, but unexpectedly, we have a lot of foreign patients visiting Korea to receive care from academic medical centers. By specialty, internal medicine, plastic surgery, and dermatology. In this order, we have the medical tourism and tourists. So there are many medical tourists for plastic surgery, but also we can see that a lot of severe patients are visiting Korea to receive treatment from major centers. Let's look at the disease breakdown: rare disease, cancer, and the cerebrovascular disease and serious burns. So growth rates of annual cases of major diseases, including cancer, cardiovascular disease, cerebral vascular diseases, and serious burns have been decreasing. So the number of patients in these specialties is decreasing in terms of medical tourism. So what is the reason? The reason is not clear. So we can only assume that the number of foreign patients has not picked up fully even after the COVID-19 pandemic. But I believe there is a great potential for recovery of the number of foreign patients in these specialties. Now, let me talk about the current status of Korean healthcare services in Korea. I would like to showcase advanced Korean healthcare services. So other speakers will also talk about advanced medical services and technologies. In dire situations in Korea in terms of medical prices, we are managing to provide really high quality medical services, including robot-assisted technology. And we also have very skilled medical professionals. But considering this, still, we offer very affordable prices, and also we have short wait time at Korean hospitals. In America and in Canada, it takes a lot of time to receive medical services. It takes about 3 months to get an X-ray done. And in Korea, the number of patients per doctor is the highest in the world, which means that medical service accessibility is the best in the world. Life expectancy in Korea is increasing very rapidly. The blue line refers to Korea. So Korea's life expectancy is increasing very much. So the babies who were born in 2022, they are expected to live up to 83 years old. Since I was born in the 1960s, I don't think my life expectancy will be that long. In comparison to Japan, I mean, Korea and Japan, compared to UK and the United States, life expectancy is consistently increasing. And during the COVID-19 pandemic, life expectancy in the UK and the United States dropped because their quarantine measures were not really effective. So during the initial phase of COVID-19 pandemic, many people died in the UK and in the United States. So I'm a specialist in respiratory medicine. So during the COVID-19 pandemic, we conducted surgeries in respiratory systems, and we felt that depending on the reaction of the host to COVID-19 virus, symptoms varied. And we saw that many people who died of COVID-19 were Caucasian. So there's more research needed to identify the reason behind a lot of deaths among Caucasians. The red line is OECD average in terms of mortality rate, and the blue line refers to Korea. So Korea is doing really good in terms of mortality rate. After the pandemic, most countries showed the increased mortality rate, but Israel, Korea, Luxembourg showed lower mortality rates even during the COVID-19 pandemic and after that. And infant mortality rate is also really good compared to other countries. So Korea's infant mortality rate is lower than other countries. So relatively, Korea's infant mortality rate is low. But what's concerning in Korea is that we have really low birth rate. So for each and every baby born, we are doing our best to provide best care. That's why Korea's infant mortality rate is really low, and also Korea's healthcare services are really advanced. For severe diseases, cancer survivor rate, I think this presentation showed wrong information. Korea's cancer mortality rate is the lowest. So Korea's cancer survival, this is not cancer survivor rate graph. This is the cancer mortality rate graph. Korea shows the lowest cancer mortality rate. We have many surgeons here in this audience. To make this difference in terms of cancer mortality rate compared to other countries, it is really hard to show this result. So we offer really advanced surgeries, and also we have really high standards of healthcare services. That's why we were able to achieve lowest cancer mortality rate. This slide is about healthcare accessibility. The OECD's, compared to OECD average, Korea's average number of doctor per patient is really low. Per capita physician rate is the highest. The per capita physician rate is 15 to 16 in Korea, while the US one is 4. So medical service accessibility is really high. So patients easily visit hospitals, and also medical costs are really low. So patients easily find Korean hospitals. And we really have shortage of doctors, but each doctor sees a lot of patients. That way we address the shortage of doctors. So we do have really great healthcare accessibility. Now I would like to talk about medical costs. Let's look at the total healthcare spending. What is the highest one? That is the US one. The US shows the highest healthcare spending. The red line is Japan. Korea is the bottom one. The UK one is between Korea and Japan. So we have really high life expectancy with the lowest healthcare spending. So we spend less for higher life expectancy. In the United States, healthcare spending is the largest. Their medical services level is really high, but they inject a lot of money too in the United States. The US spends 3 to 4 times more on healthcare than South Korea. So Korea's medical costs are the lowest. But compared to Japan and UK, patients out-of-pocket is really high. So I think it is attributed to the low reimbursement for hospitals. But still, nevertheless, Korea's medical costs are really low. How much we spend in cancer care? Korea's cancer mortality rate is the lowest, but cancer care expenditure is the 8th in the world. In Spain and UK and other European countries, the government makes sure there's a low cancer expenditure. But in Korea, we achieve high cancer survivor rates with low cancer care expenditure. This is the average cost for surgery. I'm a cardiac surgeon. Coronary bypass, the cost is that much as you see in the table. So Korea has low the treatment cost compared to the United States, but Thailand shows even lower cost. But in terms of quality and cost, Korea is really excelling. At Korea's major medical centers, Korea's medical technology and outcomes are comparable to those of the United States. Nevertheless, the costs are really lower than those in the United States. So we are really competitive in terms of prices and medical services. So now let me talk about strategies to expand medical tourism. So we have caught up with other types of diseases, but in terms of severe disease treatment, we still have more room to catch up with. So we need to train our medical professionals. We need to maintain medical prices competitiveness, and also we need to make sure we have proper interpreters at medical centers. And the government needs to provide legal, financial, and policy support. So we need to focus on the severe diseases. So when it comes to advanced medical technologies, we can think about telemedicine, robotic surgery, and artificial intelligence diagnosis. This is the story of the Seoul National University Hospital. So not only in Seoul National University Hospital, but also in other major centers, they have set up already telemedicine facilities. So right now, we have telemedicine platforms in place. When it comes to robotic surgery, we have the CEO of Da Vinci system company. So Korea is the country that has deployed and adopted the highest number of Da Vinci systems. So this is a picture of surgeons conducting robotic surgery. So for thyroid cancer, lung cancer, and esophagus cancer, we are providing robotic surgeries. At Seoul National University Hospital, we have a lot of patients with rare pediatric diseases. Later, we'll hear about CAR-T at Seoul National University Hospital. We have the facility to create CAR-T therapy. In Severance Hospital, there's a particle therapy center. At Seoul National University Hospital, in 2027, Seoul National University Hospital adopted and established the Gijang Cancer Center for heavy ion therapy. So the entire public can actually access this facility. This is a picture of myself. This baby is 2-year-old baby. The boy received the lung transplantation. So this was a successful lung transplantation case. And we conduct liver-lung co-transplantation as well. So for younger babies, we are able to provide lung transplantation. We need to maintain price competitiveness, and transparency is key. Government support is also critical. By 2027, Korea will be able to attract 700,000 foreign patients, and Korea International Medical Association will strive to achieve this goal of attracting 700,000 patients by 2027. And we will focus on severe diseases, and we will best utilize advanced medical technologies, and we will make sure the high healthcare service costs remain at proper level, and the government support is also critical. We will do our best in that regard. Thank you very much.
Thank you very much to President Kim, and we look forward to many new prospects in treatment of foreign patients, especially through strategies in medical tourism. So why don't we give him another big round of applause? And our next speaker is Dr. Mitchell Posner, Physician-in-Chief of the Comprehensive Center at the University of Chicago Medicine. And he will deliver a presentation on the topic of current advances in cancer treatment and reimagining future cancer care. Dr. Posner has been named a top doctor by Chicago Magazine 4 times since 2006 and was recognized as America's top doctor for cancer in 2013. So please allow me to invite Dr. Posner to the stage with a big round of applause.
안녕하세요. Professor Kim, after listening to your presentation, and as I get older, what I decided is I'm going to move to Korea now. So I'd like to talk with you this morning about our current advances in cancer treatment at the University of Chicago Comprehensive Cancer Center and how we're looking forward to the future and what it holds. The University of Chicago was founded in 1890. I think most people recognize us for our prestige as a research institute, and notably we've had over 100 Nobel Prize winners and 12 in physiology and medicine, 2 of which were in surgery. Our health system continues to grow. both on site in the south side of Chicago, but also expanding our network to provide state-of-the-art care beyond the Chicago city. We're recognized by external forces as a high-profile cancer program and hospital. Importantly, by the Leapfrog group that looks at safety. We are only one of 18 hospitals out of 3,000 that have received 24 consecutive A grades for safety. Our mission is to eradicate cancer through equitable prevention, innovative and collaborative research, compassionate patient care, inclusive education, and dedicated community engagement, and we are a global center for excellence. In order to maintain that excellence, we have to invest significantly in our cancer enterprise, and we are doing that. First of all, in novel therapeutics in terms of drug discovery and development and cellular therapy. We are creating a state-of-the-art cancer pavilion that will open in 2027 that I'll show you in a little while. Using adaptive oncology to provide personalized and individualized care to every cancer patient and try to eliminate the healthcare disparities that occur in our country in patients who are underserved and economically disadvantaged. In order to do that, we have to invest in our significant research enterprise, and you can see our 4 programs on the left, all of which have grown in terms of external funding and continue to grow dramatically. That is also true of our programs and our faculty, as well as our recruitments. We measure our impact of our research, obviously by the number of relevant publications, but probably more important by the impact factor that they have. And as you can see again from our one renewal, 2017, to our most recent renewal by the National Cancer Institute, our impact factor continues to grow competitively. In order to develop novel cancer therapeutics, we've taken advantage of our partnership with Argonne National Laboratory. As you may know, Argonne National Laboratory was born out of the first sustained chain reaction, which occurred on the University of Chicago campus for the Manhattan Project during World War II. And our partnership is there to facilitate drug discovery and development. Our partnership leverages Argonne National Laboratory's considerable computational capabilities, X-ray crystallography, structural chemistry, to discover first-in-class compounds based on targets that the University of Chicago faculty investigators have identified. We are expanding our GMP facilities to accelerate novel therapeutics. We're expanding our cell manufacturing facility, opening a new vector production CGMP, and a new microbiome CGM facility. And as you can see here, we have a cyclotron, which actually will be now a new one put into our new cancer pavilion that opens in 2027. At the moment, we have 4 investigational PET compounds under IND, and several radionuclide candidates for imaging and theranostic radiopharmaceuticals that are in development. Again, we leverage Argonne's expertise and facilities that are extraordinary in order to provide this new discovery and development of radiopharmaceuticals. Just to give you one example, this is the ELAINE pathway, which kills cancer cells via proteolytic release of CD95 death domain, as you can see here on the left. It is quite specific for cancer cells. And our investigators discovered N17350, which is a first-in-class biologic that mobilizes this pathway to kill cancer cells. And you can see a preclinical model here on the right that destroys tumors completely in mice. Our job is not to cure mice, though, it's to take care of patients. And the fuel for all of this science is our excessive efforts in clinical trial activity. You can see that our total accrual continues to increase over time. And there are multiple examples of practice-changing clinical trials. This one on the role of lobar resection for non-small cell cancer. This one for the combination of immunotherapy and chemotherapy in non-small cell lung cancer. Our CAR T cell therapy programs, our work in leukemia, and our work in pharmacokinetics to decrease toxicity of regimens that are delivered, especially immunotherapy. We have a very unique history at the University of Chicago. As I mentioned, there are 2 Nobel laureates in medicine. One that you may be familiar with is Charles Huggins, who is the individual who founded the connection of hormonal therapy with cancer and received a Nobel Prize in the 30s. Also, Janet Rowley was the individual who actually discovered the genetic basis for cancer in her work in leukemia. The identification of oligometastases as an entity that we now could use regional therapy as opposed to only systemic therapy in patients with limited metastases. And finally, AI detection in radiology. The prototype AI-infused mammography was actually developed by Mary Ellen Geiger at the University of Chicago that was approved by the FDA. Dr. Kunle Adansi is our director of the Comprehensive Cancer Center. I work with Dr. Smith and Ms. Washington to run the service line and the clinical aspects of the Comprehensive Cancer Center. There's no question that the future of cancer care is innovation, and any organization that wants to continue to be a leader has to constantly innovate in the following areas. As I mentioned, discovery, and more importantly, translation of new knowledge and research, prevention, early detection, and innovative therapies, and survivorship. Also, innovative practice models that I'll talk to you about with our new Cancer Pavilion, taking advantage of the emerging technology, digital technology, as well as AI to improve care processes and outcomes, as well as the patient experience. We have been a comprehensive cancer center for over 20 years and received granting from the NCI for over 50 years. We'll actually have a reception for our 50-year anniversary at this year's ASCO meeting. And what defines Comprehensive Cancer Institute by the NCI is not just the clinical care, the research, the training, and the community impact, but really the fundamental basic research that occurs in the population research, fundamental basic science, translational research, and of course, clinical research activity in the context of clinical trials. I've talked to you about our world-class capability and storied history. And in order, again, to be able to move to the future, we're making a significant generational investment in our new Cancer Pavilion, as you can see here on the right. Our numbers speak for themselves in terms of our activity in cancer. I'll point out that the University of Chicago is only one of 30 U.S. institutions that was selected as lead academic participation sites for NCI's National Cancer Trials Network. That means that to be one of these sites, you have to have more than 300 open trials, and that trial enrollment has to be more than 1,000 per year at your institution. Continued investment is critical to developing the research pipeline, and as you can see here, we continue to do that in every component of clinical trial activity. Importantly, from our aspect with our community, we actually accrue over 30% of minority patients to clinical trials, which is critical because in the past, clinical trials were focused on a very, very select group of people and didn't actually expand to the entire breadth of our community network, and we never knew if those findings that showed impact actually had impact throughout our population. Just to give you a quick view of some of our programs, in GI cancer, I mentioned oligometastases. We have a robust HIPEC program and hepatic artery infusion program, a unique trial, which I'll show you in a second, as a personalized approach to gastroesophageal cancer. In head and neck cancer, we're known as the pioneer of organ-sparing treatment for head and neck cancer with chemotherapy and radiation therapy. The picture there is of Grant Achatz, who is the chef at the 3-star Michelin restaurant in Chicago, who, believe it or not, developed tongue cancer as a chef, went to every other institution in the United States that recommended a glossectomy or removal of the tongue. He is still now a chef with his tongue at Chicago because of our efforts. First to market innovations in thoracic oncology, including advanced AI bronchoscopy. In gynecologic oncology, we were one of the few hospitals in the United States and the only hospital in our state offering radical vaginal trachelectomy to preserve fertility in patients with cervical cancer. In breast cancer, we're the only institution in Chicago offering phase 1 through 3 clinical trials. And in addition, we are one of the only institutions that are involved with lymphovenous bypass and lymph node transfer to eliminate lymphedema following treatment of breast cancer patients with surgery. Urologic oncology, we're the leading centers in the world in terms of our volume of robotic procedures for prostate cancer. Our clinical programs, I mentioned, our significant effort in cytoreductive surgery and hypothermic intraperitoneal chemotherapy, and in addition, HI therapy to convert unresectable patients with hepatic metastases from colorectal cancer to a resectable state. If you look at our outcomes compared to benchmark programs in the United States, like MD Anderson, Memorial Sloan Kettering Cancer Center, Dana-Farber Cancer Center, that had programs that were engaged for over 30 years, our program, which started 30 years ago, has superior outcomes in terms of length of stay, the use of laparoscopic HIPEC, lower readmission rates, 30-day mortality, and admissions to the ICU. This was that unique, novel clinical trial that was developed by one of my colleagues that I participated in, which takes advantage, or recognition, I should say better, of spatial heterogeneity in a cancer patient. We know there's heterogeneity in terms of the molecular genetics and mutations from patient to patient, but it's also the case in a single patient from their primary tumor to their metastases or their circulating DNA. So there's this spatial heterogeneity. In addition, there's temporal heterogeneity, noting that mutations will continue to occur. And this cascade trial, which you see here, took advantage of that. This will be difficult to see. Just to give you an example, this one patient looking at ERB2 or HER2/neu was negative with regard to the primary tumor, but both in red here you can see in the metastases and ctDNA, there was amplification ERB2 that was noted. And you can see that here, both in lymph node metastases and hepatic metastases, IHC staining for HER2, and also amplification on the right here. And what that means, you can take a patient and personally direct their therapy here with trastuzumab against HER2. You can see almost complete eradication of the tumor in a patient. We also are looking at ways to improve our prognostication. This is an analysis we did, a discovery analysis on our patients who underwent hepatic resection, and looking at consensus clustering of shared expression patterns, of gene expression patterns. We were able to identify 3 distinct molecular subtypes of hepatic metastases. And without the clinical risk, we could actually, with genetic risk, actually separate them in terms of their survival, as you can see here on the right. And then if you combine that with a clinical risk score that was developed many, many years ago, you can see we can define a subset of patients who are actually at 90% 10-year survival following a resection of their hepatic metastases, and others below. We had to validate that, so we used patient information from a randomized clinical trial performed in Europe. And again, we saw the same thing, the ability to validate these molecular subtypes based, again, purely on their shared expression genetic patterns. And we combined it with a clinical risk score. Again, you can see the separation of the curves. And why this is so helpful is that in patients with hepatic metastases who undergo resection, we know that adjuvant therapy has not appeared to be of benefit. So we can avoid adjuvant therapy in those patients who are destined to do well by this molecular classification, and in others actually try to identify targets that would improve our therapy. We also have a significant effort in a neuroendocrine program. And you can see that our patient volume has steadily increased over time, looking at mainly pancreatic neuroendocrine tumors, which is validated by organizations in the United States. And a significant effort, again, with Argonne National Laboratory and Theranostics. Again, Theranostics uses tandem use of diagnostic and therapeutic radiopharmaceuticals, which share a target protein. You can see here the radioactive compound being linked to a target molecule that is targeted to a protein on a cancer cell. We're trying to improve theranostics by a concept of true theranostics, which show identical in vitro pharmacokinetics, in vivo pharmacokinetics with in vitro binding in order to improve this kind of therapy. Therefore, again, with our partners at Argonne National Laboratory, looking at new radionuclides and radiopharmaceuticals here with scandium. And what we can do then is with this identical in vivo pharmacokinetics and in vitro binding, we can see improved congruence between PET screening and the delivery of targeted radiotherapy that we can't see with our current agents with gadolinium PSMA and lutetium PSMA. We are also, again, a leader in terms of AI in breast cancer MRIs, again, utilizing size, shape, and morphology, as well as contrast enhancement that allows us to be able to predict a malignant tumor from a benign tumor. In addition, we now can predict with MRI and AI enhancement the ability to identify recurrence, free survival, as well as a response to neoadjuvant chemotherapy. And finally, now be able to predict even the microarray expression profiles with AI, with MRI. Finally, I just wanted to show you with our significant investment for the future, our new cancer pavilion, which will be located on our Southside campus. This will be the first freestanding and dedicated comprehensive cancer center in Chicago with a unique approach to thinking and care about patients in a holistic way, from addressing their financial matters of living with cancer to managing life after a cancer diagnosis, with a fully coordinated patient and family-centric experience, multidisciplinary care that is fueled by emerging technologies and artificial intelligence. This is our new building, approximately an $825 million investment in this cancer pavilion, which will open up in 2027 with almost 600,000 square feet dedicated to cancer and bringing everything under one roof. Again, to enable our multidisciplinary care and to be able to approach our patients with a holistic approach so that their journey with cancer is actually made easy. Our differentiators in reimagining cancer care of the future is to deliver cutting-edge diagnostic and treatments for patients, apply technological advances, and actually, again, revolutionize the care delivery model and the patient experience. The concept of launch to provide a rapid multidisciplinary care to patients in a single setting, all in one effort, and enhance consultation and exam rooms, a collaborative tech-enabled team to bring family into our consultations, and the use of virtual and telehealth space, as well as robots to enhance efficiency in operations. So our commitment to clinical research and innovation is, again, to put science on display, but more important, to put it in play for every single patient who enters our institution, to embed research and discovery in the fabric of our center, and foster digital innovation and technology to enhance the patient and provider experience. As I mentioned, the cyclotron will be actually in this new cancer pavilion to facilitate drug discovery and development, to bring it to the patient's bedside. And again, all of these pharmaceuticals that are under development at the present time. So we're in a unique position because having the Cancer Pavilion and our medical center embedded in the University of Chicago, we can take this continuum of drug discovery. We can use a cancer biologist to discover a therapeutic target, a structural biologist in the Division of Biologic Sciences to determine the structure of that target. We can have a computational biologist identify multiple drug candidates, and then a chemist to modify that molecular skeleton of the drug candidate to help it do a better job. And then finally, a molecular engineer in the Pritzker School of Molecular Engineering at University of Chicago to create a nanoparticle to protect that therapy and make sure that it does its job. As I said, we're focused on patients and family first, a seamless experience, an international destination for cancer care, and looking at clinical research and innovation that is the foundation of everything we do at the University of Chicago. We've gone through a period of going through every step in a patient's journey to enhance the efficiency of care, optimize their experience, and make the journey as simple as possible. Again, I want to thank you for your attention. It's been a privilege to speak with you today. Thank you very much.
Thank you very much, Dr. Posner. It was a truly insightful presentation, and in particular, raising expectations for the Cancer Center of the Future. Let's give him another big round of applause. And next up is our third presentation. Dr. Seung-Yu Lee, Endowed Chair Professor of Asan Medical Center, will deliver a presentation on the topic Living Donor Liver Transplantation at Asan Medical Center. Now, Professor Lee is a global authority in liver transplantation who achieved the world's first 2-to-1 living donor liver transplantation in 2000. Through his passion, dedication, and excellent teamwork, he accomplished over 8,000 cases of liver transplantation, setting a record for the longest surviving liver recipient in Korea. He has consistently contributed to the advancement of medicine and the training of healthcare professionals at home and abroad, truly spreading the excellence of Korean medicine. Now, Professor Lee will deliver his presentation while seated due to his health issue, as he has already requested, so it would be greatly appreciated if you could extend understanding for that. So, ladies and gentlemen, please welcome Professor Seung-Yu Lee, who is making history in living donor liver transplantation, with a big round of applause.
Thank you very much. My topic is evolution of living donor liver transplant at our institute as a medical centers. The next slide, please. As you see, normal liver is the largest organ in our human body. Its volume is equivalent to 2% of our body weight. And the liver is highly vascularized organ, so fast regeneration occurs after its injury. And also liver is center of metabolism, one of the most important organs in our bodies. Next, please. But liver injury, as the end-stage liver cirrhosis, showed small contracted liver. Spleen is enlarged and the massive ascites developed, and the varix bleeding and hepatic encephalopathy and coma may develop. In this stage, Patient remaining lifespan is less than 6 months. Then this CT finding is indication of a liver transplant. Next, please. Left side CT is before liver transplant in the compensated cirrhotic patient. Right side CT shows after liver transplant. Ascites is all gone, and this is small contracted liver is replaced with big healthy livers. Patient dramatically recovered. So, acceptance of liver transplant as a standard treatment for end-stage liver disease. Next slide, please. From early 1990 has led to the exponential increase in demand of liver transplant, resulting in, next slide, please, and next, please. Resulting in increasing gap between waitlist patient and performance of diseased donor liver transplant. And half of this gap group patient die within around 1 year because of donor organ shortage. Next, please. Next, please. Disease donor liver shortage was especially serious in Asian countries, especially Korea, Japan, Taiwan, and Hong Kong, where requirement to liver transplant was highest because of a higher virus carrier rate and the higher prevalence rate of HCC and hepatitis B virus cirrhosis. Next, please. This shows seriousness of disease donor organ shortage in our early period of liver transplant. At the Asan Medical Center, disease donor liver transplant started from 1992. Living donor liver transplant started in 1994. And now, yearly, liver transplant number reaches almost 500. I wanted to show how serious disease donor liver shortage was in early 1990s and even in early 2000. In 1992, disease donor liver transplant number was 3. However, 10 years after, in 2002, marked with the green bar, disease donor liver transplant number remains static, only 4 transplants a year, in contrast to repeat increase of living donor liver transplant, 137. Next, please. Before going to my main talk, I briefly introduce liver transplant type. There are 2 kinds of liver transplant according to the donor. Living donor liver transplant and disease donor liver transplant, and each has pros and cons. Living donor liver transplant has 3 cons compared to disease donor liver transplant. First, living donor liver transplant procedure is technically complex because of small vascular and bile duct structures. Accordingly, recipient surgical complication is high. Second, liver graft size often small by its partial size. And third, live donor morbidity, even mortality exists. Next, please. Therefore, margin of safety of recipient in adult living donor liver transplant is narrow than full-size graft disease donor liver transplant. So many centers, especially in the West, where they have a relatively enough number of disease donors, are reluctant to accept the living donor liver transplant as a major form of liver transplant. Next, please. But in the West, we did not have a choice, only had to depend on living donor liver transplant. So one makes margin of safety narrow. There are 4 pitfalls: small graft size, high biliary stricture complication, and portal flow still syndrome and outflow obstruction, especially in right lobe graft. Asan Medical Center has repeatedly challenged to these 4 pitfalls during our living donor liver transplant journey. Today, I'll talk 2 issues: small size graft and outflow obstruction. Next, please. Because liver can be surgically divided into 2 functioning units as right and left lobes. So, living donor liver transplant is anatomically possible. Next, please. In the East, where viral hepatitis is endemic and the disease organ donation rate is lost, Asian countries have the greatest need for living donor liver transplant. Next, please. Although this donor liver transplant was initiated in the West 10 years earlier than the East, but the living donor liver transplant was initiated earlier from the East. In 1989, pediatric transplant in Australia. In 1993, adult living donor liver transplant from Japan. Next, please. And issues in the living donor liver transplant is quite different from deceased donor liver transplant. Issues are ensure live donor safety and avoid small size graft to ensure recipient good recovery. Adult living donor liver transplant was initiated in Japan by small size left liver lobe for the anxiousness of donor safety. Next, please. This Kyoto University experience showed that left lobe living donor liver transplant, mostly small size graft, especially graft recipient weight ratio is less than 0.8, showed poor outcomes. 3-month survivor was only 54.5% poor. So, left lobe living donor liver transplant did not spread widely to the world. Next, please. And especially look at the cons of small size graft are small size graft may develop hepatic failure, and the small size graft cannot tolerate post-transplant surgical and medical complication, and cannot apply to high MERD and the severely diseased patient. So, constant focusing in adult living donor liver transplant was directed to avoid small size graft. Next, please. Emphasizing again, first requirement for the success of adult living donor liver transplant is, before slide, go back, adequate liver graft volume to avoid small size graft. Next, please. So to overcome small size graft from using left lobe graft, then right lobe graft was introduced from, next please, from Hong Kong first, the next year at Asan, then Kyoto, and Germany and United States. Next, please. Great advancement of bigger size right lobe graft living donor liver transplant is right lobe living donor liver transplant enables donation from donors smaller in body size and recipient with more than 0.8 graft weight ratio in most instances, and has markedly increased performance of adult living donor liver transplant throughout the world. Next, please. And this shows pros, advantage of right lobe living donor liver transplant. Donor, wife, was smaller than recipient, and on 14th day post-transplant, they recovered well and looked happy. Then, all world liver transplant centers then focused and turned to right lobe living donor liver transplant from the previous left lobe living donor liver transplant. But, next please. New, unexpected issues emerged in ongoing right lobe living donor liver transplant experiences. First was donor death, but the inappropriate excessive liver volume resection. Next, please. At least 30% of total liver volume should be a remnant liver volume in the donor to ensure donor safety. But each donor shows a different volume proportion of right and left liver lobe. So appropriate donor selection is important for donor safety. Next, please. By inappropriate excessive right lobe resection in donor mortality began to report it. Next, please. Then up to 2019, 36 donor mortality were reported in all of the world, especially after right lobe living donor liver transplant. Europe 8, United States 6, Japan 1, Korea 1. Of course, it's not happened in ASEAN, but actually, unreported mortality will be more. Next, please. So, first priority in living donor liver transplant is complete donor safety. Safe donation after right lobectomy is ensured when the estimated remnant liver volume is more than 30 to 35%, depending on donor age and the degree of liver steatosis. Next, please. But there was an unhappy event of donor death in the United States in 2002. Before donor death, living donor liver transplant activity gradually increased. 524 living donor liver transplant a year in 2001. But after donor death event, living donor liver transplant activity has been going down, less than 300 living donor liver transplant a year, and cannot recover to the previous activity. Next, please. In living donor liver transplant, we should ensure both successful recipient recovery and complete donor safety. From now on, I'll talk about two world first living donor liver transplant procedure to achieve complete recipient recovery and donor safety simultaneously. Next, please. Second emerging issue was small for size graft is developed even in right lobe living donor liver transplant. If sizable V5, V8 is outflow branch of anterior sector of liver right lobe are not reconstructed. This was first reported, next please, by Asan in 1999, Journal of Korean Transplant Society, with introducing strategy to solve this complication. Next, please. For better understanding, let's look at the outflow drainage of liver hepatic veins. Central portion liver right and left lobe has to share the outflow with one middle hepatic vein. Anterior sector of right lobe drains to middle hepatic vein, and also medial sector of the left lobe also drains to middle hepatic vein. By the way, in living donor liver transplant, donor safety is top priority. So middle hepatic vein should be left in donor side in right lobe living donor liver transplant. Next, please. Consequence of preserving middle hepatic vein to donor left lobe is congestion of anterior sector of the right lobe develops. This congestion part cannot function in right lobe graft, so even if large size right lobe is transplanted, actually functioning hepatocyte volume is confined to good colored posterior sectors, so eventually small foot size graft syndrome develops. Next, please. Asan Medical Center first reported the significance of anterior sector congestion in right lobe living donor liver transplant caused by the ligation of V5 and V8 middle hepatic vein branches during donor operation. Although graft size is critical for successful outcomes, the importance of good venous outflow drainage of anterior sector of right lobe graft is crucial for maximizing functioning graft volume and the patient uneventful recovery. Next, please. Pitfalls of adult living donor liver transplant are small size, high biliary stricture, and portal flow steal and outflow obstruction, especially using light lobe graft. Our challenge to outflow obstruction was a milestone of light lobe living donor liver transplant and escalating previous 60% success rate to more than 90% success rate. Next, please. And the modified light lobe graft is making new artificial middle hepatic vein using interposition vein graft. Next, please. This is intraocular picture of a first successful middle hepatic vein tributary V5 V8 reconstruction using patient own great saphenous vein. Next, please. And next, please. Before reconstruction, severe congestion was shown, but after V5 and V8 reconstruction, congestion, respect to previous slide, congestion soon disappeared. And next, please. This modified light graft using cadaveric cryopreserved vena cava interposition graft. And next slide, please. This modified light graft is using synthetic vascular graft. Our modified light graft has become a world standard light lobe living donor liver transplant procedure, remarkably elevating success rate of adult living donor liver transplant and also ensuring donor safety by preserving middle hepatic vein in donor remnant left liver lobe. Next, please. Thereafter, modified light lobe graft has emerged as a practical option to reduce waitlist mortality in the East. However, all potential donors, especially light lobe, are not accepted. Next, please. So, to overcome small size graft without endangering donor safety, okay, thank you. we have to reconstruct middle hepatic vein tributary. And next slide, please. And then after modified light graft, we invented dual transplant, especially when donor has small left lobe and a large right lobe. In these instances, when we harvest large right lobe in the donor may die due to hepatic failure caused by the excessive liver volume resection. And this is the view of world first dual living donor liver transplant using a small sized liver left lobe. And next, please. And the goal of two left lobe dual transplant arose from first donor safety issue, and then provide adequate liver graft size and prevent small for size graft syndrome, and also to increase expanded donor pool by optimal use of the marginal graft, such as small size graft of a steatotic liver graft. Next, please. Next. This is the very important principle in living donor liver transplant. Donor safety is first priority, so safe donation after right hepatic in the donor is possible only when estimated the liver volume is enough, more than 30 to 35% their total liver volume. Next, please. This shows dual living donor liver transplant using dual two left lobe. And next, please. And this is operative view of the dual living donor liver transplant. There is a two small left lobe in the patient abdomen. And next, please. And the first left side left lobe graft was anastomosed. And next, please. And the right-sided left lobe graft was anastomosed, and the portal population was performed. Next, please. This shows fast graft regeneration of two left lobe dual graft transplant. Left side is preoperative view of hepatic decompensation in the donor, and then middle is the post-dual 1 week, and the right side is post-dual 3 weeks. It looks like normal liver shape and size, fast regeneration, then single graft transplant. Next, please. And most frequent question to dual living donor liver transplant is donor risk will be higher in dual transplant because two donors are undergoing surgery, but donor risk is proportionally increased by resecting amount of liver volume. So donor risk is much less in dual left lobe transplant than in moderate right lobe donor hepatectomy. Next, please. Review again pros and cons of dual transplant. Pros is certain outcome by abolishing small size graft, and optimal use of marginal graft is possible. And dual transplant is also applied even to high merit, seriously ill patient. But cons is we have to need double donor resource, and this is a little technically demanding. In this theoretically double surgical complication, but it is absolutely based on theoretical concept. And lastly, long operation time is also one of the cons of dual transplant. Next, please. So by the long operation time, anesthesiologist eyes, he is standing second from the left. His eyes almost are closed, and the surgeon looks tired. But visitors from Turkey and United States looks happy. And next, please. Beside the dual left lobe transplant, this right side picture shows right and left dual transplant. And next, please. This right and left liver transplant is necessary when donor body size are much smaller than the recipient. Then right and left lobe dual transplant is a good strategy to avoid small for size graft syndrome. Next, please. This was the first successful dual right and left transplant was performed in 2001. Recipient body size was big, 188 centimeter high and 90 kilogram, but donors was small body sized. Wife was 60 centimeter high, 51 kilograms small. Cousin, 173 centimeters and 62 kilogram, but has small left lobe. I think this right and left lobe dual transplant requirement maybe it'll be high in America because American's body size is larger than Korean. Yes, please. And this right and left dual transplant was dealt in cover story of 2015 American Journal of Transplant. They showed much attention to these procedures. Next, please. Until 2022, 609 dual transplant was performed. Dual left lobe transplant 353, right and left 256. Their outcomes is comparable to single right lobe driven donor liver transplant and full-size disease donor liver transplant. Next, please. This was television news report of the world first dual left lobe transplant Donor was from daughter and brother. Next, please. And the patient is good now, 24 years afterward the first dual transplant. Next patient is his donor daughter. Asan innovation, next please. Oh, before, go back. Asan innovation contributes to save many patients' lives by Asan's way. Next please. Dual living donor transplant proportion is around 7 to 8% of all adult living donor transplant, often very practical in particular instances. Next, please. This shows world performance of liver transplant. Deep green bar shows diseased donor liver transplant. Light green bar shows living donor liver transplant. Although living donor liver transplant is a technically complex procedure than deceased donor liver transplant, in the East, living donor liver transplant is favored alternative to deceased donor liver transplant because of the deceased donor liver shortage. Then, next please. Why adult living donor liver transplant is increasing in Korea? Despite of its technically demanding procedure and the potential live donor risk, there are many reasons. Among these, technical advancement of surgery and acceptable result of recipient donors are main reasons. This is Korea's first living donor liver transplant. Next, please. Next, please. In 1994, for biliary atresia, 9-month-old child. Next, please. Grow to lady after living donor liver transplant. Now she is left side. She is 30 years old after transplant and healthy. And this year, December, we are preparing 30-year ceremony for her good health after living donor liver transplant. Next, please. This is Korea's first adult living donor liver transplant using left lobe graft for unresectable multiple liver cancer. He is now good working as lawyer. Next, please. Good outcomes of transplanted patient has a good provocative effect to increase transplant number. In 2017, we performed 361 living donor liver transplant, 349 adult, 12 pediatric patients, and it is said that surgeon's challenge to zero operative mortality is a dream. Next, please. But zero in hospital mortality in living donor liver transplant, it was my old long dream, was achieved, even though 20% of our patient was high risk, high MELD, and ICU bound, and the 25% was technically complex dual living donor liver transplant. Next, please. And our indication of living donor liver transplant is same as diseased donor liver transplant. High MELD and the seriously ill patient all are accepted for living donor liver transplant. Next, please. Now I would like to summarize and conclude my talk. Adult living donor liver transplant has many cons compared to diseased donor liver transplant. Cons: donor risk or small size graft, and this is technically demanding, but has many advantages. Pros: it has a larger donor pool, so waitlist mortality can be decreased. Especially, timely operation is allowed to save critically ill, urgent, or emergent patient. Next, please. This acute liver failure patient underwent emergency dual transplant before progressing irreversible brain swelling and she recovered well. Living donor liver transplant, before go back, gave opportunity of timely operation for this highly urgent patient. Next, please. This is my last slide in adult living donor transplant. Margin of safety of recipient is narrow, then this is donor liver transplant because it is technically challenging. And the living donor liver transplant demand more surgical skills and experience and the right philosophy of surgeon with challenge to obtain the best result and to minimize morbidity and mortality of the patient. Furthermore, often living donor liver transplant operation time is long compared to deceased donor liver transplant. But dedication of a medical personnel is rewarded by patient life-saving. Thank you very much for your kind attention. I want to show next slide. They underwent living donor liver transplant at our institute. They are from UAE. And beside this male patient, there are many female patients, but their culture does not allow women sit together with men. And next slide, please. And the outreach operation also was performed. This is 2002. I visited Turkey, and I succeeded. Turkey first living donor liver transplant in Izmir. Next, please. And also, we are learning assigning Asia project to our neighboring developing country. In 2011, Mongolian first liver transplant by adult living donor liver transplantation. And next, please. And also, all over the world, many young surgeons visited to ASEAN to learn our living donor liver transplant strategy, and we are happy to contribute our surgical strategy to all over the world. Thank you very much for your kind attention.
Thank you very much, Professor Lee. Thank you for introducing the various different cases of transplants. And we hope in the years to come, we will see a hike in successful liver transplantations. Let's give Professor Lee another big round of applause. And now it's time to move on to the fourth presentation. On the topic of cutting-edge strategies in hematologic malignancies, unveiling the power of cell therapy, including hematopoietic stem cell transplantation and innovative CAR-T therapy. Professor Ki-Sung the head of the Lymphoma Center at Seoul St. Mary's Hospital of the Catholic University of Korea, will hold this presentation. Professor serves as a hematologic oncology specialist and is currently the clinical department head of hematology at Seoul St. Mary's Hospital. He also holds the position of chairman of the Advanced Regenerative Medicine Committee at Catholic Hematology Hospital, actively participating in the introduction of CAR-T therapy and engaging in vibrant activities related to cell therapy. So let's welcome him with a big round of applause.
Thank you for the introduction. I work in the Lymphoma Center of the Catholic Hematology Hospital at Seoul St. Mary's Hospital. So my presentation will be focused on cell therapy, especially the cutting-edge technology of CAR-T cell transplantation, as well as HSLT, hematopoietic stem cell transplantation. When we talk about cell therapy, we have to talk about Emily White. In 2010, Emily White became acute lymphoblastic leukemia. The parents were in despair, and oncologists said that if I want to have one cancer, if I can choose one cancer that I have to get, I would choose Hodgkin's lymphoma or acute lymphoblastic leukemia, but unfortunately, there was a relapse in 6 months, and the physicians recommended stem cell transplantation, which was refused because of concerns of complications, and chemotherapy was administered. So when you look at the result after 6-month relapse, 1-year survival is less than 20%, which is very dismal. In 2012, at the Children's Hospital of Philadelphia, the child received CAR T-cell transplantation called Kymnia, and she's cancer-free at the 3rd year, still cancer-free at the 5th year and the 10th year. And this is the picture taken from May 2022, and she's very healthy even now. She was the first pediatric patient to receive CAR T transplantation in the world. The 1st-year outcome, when you look at the line, the 6th-month survival is around 40%. But with cell transplantation using CAR T therapy, this has risen to 70%. In terms of cell therapy, we always talk about hematopoietic stem cell transplantation, in short HSCT, which is not very innovative compared to CAR T transplantation. It's been used for more than 50 years around the world, but HSCT needs to be discussed because it still, for many different illnesses, remains the only cure. So living cell is used to treat cancer when we talk about cell therapy. We have also immune cells in our body, or modified cells at the lab level that targets the cancer cell in the body and kills the cancer cell under cell therapy. And you also have HSCT under the stem cell-based cell therapy, and CAR T therapy is also being used very often. And they are the most common cell therapies used right now around the world. Still, as mentioned, HSCT remains the only modality to cure various illnesses, including acute myeloid leukemia, acute lymphoblastic leukemia, chronic lymphocytic leukemia, and chronic myeloid leukemia, as well as benign disorders, for example, thalassemia, sickle anemia, and aplastic anemia. So this is the process of analogous HSCT. So you only get the hematopoietic stem cell and transplant this through the vein, and it will be circulating and it will be attached to the bone marrow. But it doesn't succeed only when we just inject the cell to the bone marrow, because there's also rejections. So we need radiation therapy in order to destroy the immune therapies. So this is the analogous stem cells transplantation. And in order to overcome the negative side effects, we also can use autologous stem cell transplantation in contrast to allogeneic transplantation. So the dose of the cancer drug, as it increases, more cancer cells will be destroyed. So very high dose treatment will be administered, but higher the dose, The first irreversible change you will see is the damage to HSC. Above a certain threshold, there would be permanent damage to HSC, which means that HSCT will become meaningless. So after a high-dose treatment, when the cancer cells are destroyed, HSC will be destroyed. So a normal hematopoietic function will not be carried out. So a process to restore the HSC will be needed, which is none other than HSCT. So this is one therapy to overcome the risk that is ensued by the bone marrow transplantation using autologous stem cells. When we carry out allogenic transplantation, we thought cancer cells are killed with radiation. But when you look at leukemia and lymphoma, we understand that immune cells, when HSC is injected, it will create more immune cells, and immune cells will be the main function, killing the cancer cells. So that there's the graft versus tumor effect, or graft versus lymphoma effect, that is the main mechanism to kill cancer cells. But there's also the graft versus host disease that attacks the liver or skin. So the same T lymphocyte could attack a normal cell. So we would use immunosuppressant in order to restrain the GVHD. And with allogenic HSCT, there's a lot of complications such as infection, graft failure, and various malfunctioning of the organs. That happens at the T lymphocyte and immune cells. So we want to target the cancer cell in order to distinguish between GVHD and GVL, but there is no way to do this right now. So transplantation mortality is between 10 to 15% without the relapse of lymphoma and leukemia. And during transplantation, you need to consider the donor. We say HLA, human leukocyte antigen, and we need to have the matching HLA to be able to carry out transplantation. HLA, ABCD are the 4 genes and 4 antigen and 8 genes must be matched. So if the donor is your parent, well, if you share the same parent, there is 25 possibility that you're going to meet a matching donor among your family. But it's hard to find matched sibling donors these days. So we use the unrelated donor registry to carry out transplantation these days. So the main way was unrelated donor transplantation with 8 out of 8 matching. But nowadays, we can carry out transplantation even when only 6 out of 8 genes match. But there are cases where you don't have any children, and then you would use cord blood transplantation. So right now, theoretically, there's no case where we cannot carry out allogenic HSCT because you don't have any family. And currently in Korea, we have around 400,000 donors registered in our registry, and globally there are around 90,000 cases of allogenic HSCT. In Korea, the number of cumulative cases starting from 1984 has been rising, leading to around 48,000 cases. So annually, we see 3,000 cases in Korea. So nowadays, we carry out unrelated transplantation, and when you look at the outcome, this is the data from the Catholic Hospital, St. Mary's Hospital. You can see the survival rate, months after transplantation, DFS, and there's no difference between matched sibling donor and matched unrelated donor transplantation. And relapse and mortality, they don't show any difference between the two cases. And acute graft versus host disease also shows no difference between the two cases. So nowadays, we can safely carry out unrelated matched donor transplantation. And there are cases of related matched donors and unrelated donor transplantations where only half of your genes match, and overall disease-free survival and relapse, non-relapse mortality, and GVHD-free, relapse-free survival show not a big difference between the two groups. So when you make a comparison, related matched donors would be the best case, but still looking for unrelated matched donors or half matching donors don't really cause a problem because there's no difference in the outcome. And this is the history of the Catholic Hematology Hospital. In 1983, the first allogenic stem cell transplantation was carried out here in Korea. After that, we successfully carried out unrelated stem cell transplantation and many innovative cases in Korea, and the first HSC transplantation as well. And in December 2022, we achieved 10,000 patients that underwent successful HSC transplantation. So this is the achievement of our hospital. A number of cumulative cases after 1983 has been around 10,000 in our hospital, which is 21% of cases in Korea overall. And annually, we carry out around 508 surgeries, so we take account for around 18% overall. And when you look at the data from various organics, compared to small volume transplantation centers, large volume centers have better success rates. And you can also see the survival probability. And this shows that experience is important for HSCT. What's interesting is that from the overall cases, around 70% are allogenic SCT, and the number has been growing. Comparing with other organizations in Korea, most centers carry out only 50% with allogenic. But in our case, the ratio is 70%. To make a comparison with prestigious hospitals in the US and other countries, well, this is data from 2017, and the number of cases was around 500 at that time, but it has grown to around 600. And just for allogeneic stem cell transplantation, we've carried out more than 830 cases in 2 years. So globally, also, we are one of the leading centers. Outcome is also important. Here you can see the data from Center for International Blood and Marrow Transplant Research. And we submitted an annual report of our outcome to the research center. And this is a comparison of the 3-year survival for various illnesses. And with acute myeloid leukemia and acute lymphoblastic leukemia, we are showing good results. And also with various other illness subtypes, we are showing a better score compared to the average score of organizations under CBMTR research. So from 2019, for about 5 years, we have been attracting 300 to 400 patients from overseas. So on a cumulative basis, we have carried out transplantation for 1,500. We have signed an MOU with UAE, so we have a lot of patients for this transplantation, and mostly 13 countries and their nationals visit the center. And moving on to CAR T cell therapy. CAR means chimeric antigen receptor. T lymphocytes play an important function for immunization against cancer. So through HLA, T cell receptor must be able to detect HLA in order to kill the cancer cell. But to survive, MHJ molecule is not down expressed. To overcome this issue, CAR was used to recognize the antigen. It does not use T cell receptor. It uses chimeric antigen receptor instead. This is an antibody generated from B lymphocyte, and T lymphocyte kills the cancer cell. So naturally, the cell from T lymphocyte and the antibody from B lymphocyte is combined. So that's why this is called chimeric antigen receptor. So here you can see how a chimera looks like with the body of a lion and also wings. So the tumor cell is recognized by the antibody from the B lymphocyte, and the killing is done by the T lymphocyte. So the second generation CAR T cell is being commercialized, and there's index generation carried out for the 4th generation CAR T cell. And when you look at the process from the patient, we would get T cells, and unnecessary cells will be restored. The gene for CAR will be injected in the cell using a virus. So cells that express CAR will be collected and grown. And in order to activate the T lymphocyte, a light level of cancer therapy will be carried out. And the problem is vein-to-vein time is around 3 to 5 weeks. So CAR T cell therapy transplantation is used for very serious cases, and waiting for 3 to 5 weeks becomes a big problem because the MHC material must match, and it means we cannot use allogenic T cells. because it causes a risk to the host. So here, CD19 is mostly expressed on the surface of the antigen from B cell. And if CAR detects CD19, T cell will be activated. And when T cell kills cancer cells, it releases cytokine, perforin, and granzyme. CAR T cell products approved by FDA include Tisagen, Lexucel, and Exicaptazine Silolucel. And these are approved for usually diffuse large B-cell lymphoma. And there's Kymriah and Yescarta that's most popular. And in the US, the price is around 400 million won for one injection. In 2022, Kymriah for diffuse large B-cell lymphoma, especially with patients that have experienced 2 failures, were approved. So out-of-pocket cost would be around 5 million to 6 million won per treatment. And these are non-responsive patients. Even the 4th round of treatment was non-responsive. And this is a patient showing tumor mass, showing no effect from radiation therapy. So CD19-directed CAR T cell was infused in July 2023. And here you can see that the tumor masses have been disappeared, and this patient still survives. So with CAR T cell, what level of outcome can you anticipate? This is from overseas statistics, and there was a 3-year outcome that showed complete disappearance, and 31% showed no relapse, and the median time is around 11 months for survival. And usually the patient showing great outcome is usually patients with complete disappearance at 3 years and 6 months. This shows a good prognosis for the future. So that was the case for the diffuse large B-cell leukemia. And this is a comparison with allogenic transplantation. And we looked at overall survival and event-free survival without any relapse and without any residual illnesses. And for overall survival, there is a much better outcome with Kymriah. So you spend 360 million won, and the outcome of 30% may not seem a good outcome. But let's look at this. Let's say there are 300 patients with DLBCL, and we say 200 are cured with RCHOP, and there are 50 subtype lymphomas, and 30 to 40% experience refractory DLBCL, and in 100 patients it relapses. Means that they need more intensive treatment, and around half of them are very old and high risk. So intensive treatment can cause an issue. So the remaining 50% will be subject to intensive therapy, and they also need analogous transplantation. So in the end, they would have to go to auto HCT, and in order to show efficacy, you need to respond to salvage therapy, which is around half of the people eligible for transplantation. That means 25 people, and only 40% shows long-term PFS. So it means only 10 patients can be cured. So the ratio is less than 10%. So CAR T-cell therapy and its outcome of 30% in an absolute term can be dissatisfactory, but when you look at the outcome of other treatment, when you compare 10% with 30%, you get a threefold higher survival rate. And in St. Mary's Hospital, we have started the transplantation for pediatric patients as well, and the 1-year survival was around 50%. And 1-year event-free survival and progression-free survival was around 45.4%. And here you can also see the survival rate is around 45%. Without progression, 43%. So of course, these outcomes are not satisfactory yet. So to enable improvements, a lot of bio-venture companies are making efforts to develop new methods around the world. So I showed you several CAR T-cell therapy products approved by FDA, and no other products were approved after that. They are usually under the first phase or second phase clinical trial. So there are a lot of attempts made by organizations, and let me introduce some of them. So in the case of diffuse large B-cell lymphoma, CD22 or 19 are expressed. And if you use CAR T-cell targeting only one of them, the cancer cell, in order to survive, downregulates the expression of CD22 or 19, so there's a loss. So there can be a relapse. So you can use 2 CAR T-cells targeting different genes, or you can also use a dual CAR or tandem CAR. Another way is to activate the cytokine of T-cell or proliferate T-cell, where the gene that can generate cytokines, thereby improving the CAR T-cell function. Other attempts are about myeloid leukemia, and CD33 antigen is also important. So you want T cells that target CD33. But the problem with this is that CD33 is expressed for HSC. So if you use CD33 targeting CAR, it may also kill HCS. So CD33 knockout hematoid must be transplanted at the same time, and then you would move on to using CD33 targeting CAR. This is being under research. And this is a way to save normal cells. So only one between T or B cell will be expressed. But if both needs to be expressed, it could create a better benefit. Another way is using oncolytic virus that only grows in a cancer cell and using CAR macrophages, activating the macrophage. One of the reasons leading to a failure of CAR T-cell transplantation, well, here you can see PDL1. To survive, the cancer cell and its surface programmed death ligands are expressed. And the PD-1 receptor would receive this signal to regulate T cells. Normal cells use this defense mechanism to protect itself from T cells. So the cancer cell uses this to make the T cell invalid. In order to prevent this issue, new attempts as such are being used. The T cell will detect PD-L1 and there are molecules activating signal transmission, so it would prevent the regulation effect. Or PD-1 expression may be prevented by using RNAs. Another way is to over-releasing cytokines called TROP. So this is also being actively researched. The biggest issue with CAR T therapy is cytokine release syndrome. When it kills the tumor cell that activates many cells, interferon 6-1 and interferon gamma, and other cytokine will be released, leading to fever or lowered blood pressure or hypoxia, various dysfunctions, multi-organ dysfunctions as well. In serious cases, mortality reaches 2 to 3% after CAR T therapy. So there are a lot of safety strategies being used. It expresses EGFR and also injects antibody at the same time. So it kills the CAR T cells expressing these. And ICASPR9 will be used to regulate T cell. And new types of safety switches are used. So the DNA replication of the CAR T cell would be inhibited. And this is a way to overcome the cytokine release. We also are researching the area of using natural killer cells because T cells are expensive, it takes a long time, and if the patient has been overexposed to cancer therapy, there is a lower outcome, and the patient needs to wait for 3 to 5 weeks. And if there could be GVHD due to using a different person's T cell. So many organizations are studying the way of using NK cells. NK cells are much safer than T cells. There's no GVHD and cytokine releasing syndrome. And it could be used off the shelf because there's no cytokine syndrome or GVHD. So as soon as the patient walks in, you can inject the natural killer cell. The NK92 is the only commercialized NK cell that can be used for cell therapy. So we have created a cell line, and on a 20-day culture basis, it grows 280% faster. And when we carry out in vivo animal tests, cytotoxicity of tumor cell was almost the same. So we're using NK101 cell for this study. And we use the general NK cell as a platform. And usually use viruses to inject genes to a CAR. But there could be virus-induced negative effects. So electroporation can be used here to deliver MRI. So from mRNA, CAR molecule will be generated immediately. So one step is eliminated. So it would be the same or similar method of using mRNA vaccines for coronavirus. The advantage we think is that there would be a cost reduction effect. It won't be hundreds of millions of won, it would be several single million won. And culture takes less than 1 week. It only takes about 4 to 5 days, so you can save an extra 2 to 3 weeks. And it doesn't use viruses. And multi-targeting CAR can be easily produced by using mRNA. So we're focused on CAR NK study, and we're preparing for a clinical study right now. So these are Korean CAR T therapy. There are a lot of Korean companies studying this area in the lab, and also we have a lot of Korean companies studying CAR NK cells. So this concludes my presentation. Thank you.
Thank you for that excellent presentation, unveiling the power of cell therapy, including through the introduction of the CAR T therapy. Let's give Dr. Another big hand. And the fifth presentation is about minimally invasive cancer therapy, particle therapy status in Korea, and future prospects. Dr. Hee-chul Park, director of the Proton Therapy Center at Samsung Medical Center, will deliver this presentation. Professor Park currently serves as the chairman of the Korean Society for Radiation Oncology and is an expert in non-surgical local treatment for liver cancer, specializing in radiation surgery and proton therapy. Starting in 2015, Samsung Medical Center achieved a milestone by completing 5,000 cases of proton therapy as of 2022. Professor Park is at the forefront of assisting not only liver cancer patients, but also many others to return to normal life. He plays a crucial role in establishing the Proton Therapy Center at Samsung Medical Center as the world's best institution for proton therapy. So please welcome him with a big round of applause.
Thank you for your kind introduction. I think it's nearing the lunchtime, so I'm going to speak really fast to finish on time. Today, I'm going to talk about proton therapy out of many particle therapies. I think the estimated number of new cancer patients will increase, and it will also followed by higher mortality rates. Another big problem is among the increasing cancer patients, there will be more portion of aged patients. Traditional cancer therapies, such as radiotherapy and surgeries, I think these traditional therapies are not appropriate for those aged cancer patients. There are cancer treatment modalities in the past. It was very aggressive therapy. Cut, burn, and poison. They are the main ways to expedite the death of cancer patients. But nowadays, the modern high-precision cancer therapy is leading to a lot of recoveries of cancer patients. So against this backdrop, the radiotherapy is also increasing. So about 50% of cancer patients experience at least one time of radiotherapy during their treatment journey. In the European countries, about 50% of cancer patients are indicated for radiotherapy, but the application rate of radiotherapy is lower than the ideal level. I think it depends on the infrastructure and the facilities and economic power and everything. Let's look at the situation in Korea. This is the statistics from the early 2000s. So every year we see 200,000 new cancer patients. But when you look at the annual radiotherapy patients, so about 50,000 patients are receiving radiotherapy in Korea. So the radiotherapy application rate is about 25%. When you look at the graph on the right side, from 2017 to 2019, you see the data here. So the radiotherapy application rate increased by 5% to 30%. So on the left side, you can see the details of utilization of radiotherapy. The breast cancer, lung cancer, and the urological cancer and colon cancer. This is the order of the cancers where the radiotherapy is mostly used. So for breast cancer, the RT application is really high. So radiation therapy has really wide spectrum. The traditional radiotherapy includes the usage of X-ray and gamma ray. But on the right side, you can see the proton and carbon ion therapies. They are also part of radiotherapy. So proton therapy and carbon ion therapies, these are the representative particle therapies. So radiotherapy has progressed a lot. When you look at the bottom left, when you look at the X-ray picture, you can estimate the location of cancer. So you block the other areas so that radiotherapy doesn't reach the healthy part. And the middle picture shows the CT scan picture. This is the progress from X-ray picture. So there's a gamma knife surgery for brain cancer. So we can conduct that kind of radiotherapy in any part of our body thanks to the advancement of technology. There will be advancement of equipment. So radiotherapy combined with the MRI and many hybrid therapy equipment will show up. You can see the proton therapy equipment. Even at a small clinic, this the proton equipment can be used. And the particle therapy requires a big space. So there are many different types of particle therapies. So let's watch one video which shows the basics of proton therapy. Why don't you play the video?
Since its discovery in 1895, X-rays have been used widely to treat cancer. However, X-rays also damage normal tissues in the process of reaching cancer tissues, and side effects of radiation are inevitable. Proton therapy minimizes the side effects of radiation therapy, a physical phenomenon when the body's energy absorption reaches its peak when the proton beams reach the cancer tissues. Proton therapy utilizes the physical properties of proton beams called the Bragg peak. The energy transfer to the body reaches its peak when the proton beams reach the cancer cells and disappear completely, impacting only the cancer tissues with an enormous amount of energy. It minimizes damages or side effects to healthy tissues around the tumor site. This is why proton therapy can be the next generation radiation therapy. The biggest advantage of proton therapy is that it is capable of precise treatment with 1 millimeter accuracy to the tumor site. And as the location and shape of the tumor varies by patient and even changes position according to the patient's breathing, SMC provides a treatment plan that is customized to each patient. Proton therapy minimizes the amount of radiation emitted to normal tissues surrounding the tumor, minimizing side effects and complications. Because there is almost no impact on a patient's daily life during the treatment period, the treatment doesn't require hospitalization. In the long term, it also minimizes the risk of secondary cancers caused by exposure to radiation. While conventional radiation therapy can't be repeated on an area that was once treated with radiation, proton therapy protects healthy tissues and can be applied multiple times. The safety of proton therapy has already been proved with over 100,000 patients treated worldwide. And it can be applied on almost every type of cancer, including liver, lung, head, and neck cancers, as well as brain tumors and spinal cancer, which are especially risky to operate on. Because proton therapy minimizes the body's exposure to radiation, it is especially beneficial to children with cancer as it minimizes risk of secondary cancers and impact on growth.
So the radiation therapy consists of the traditional X-ray therapy and the proton therapies. So when you look at the right side, when you apply the particle therapy to liver cancer, the surrounding normal tissues exposure to radiation is minimized. This is the real case. And we also have heavy particle therapy as part of radiotherapy. The basic principle is the same. So when you look at the media coverage, it seems like the heavy particle therapy is always better than other types of radiotherapy, but it all depends on the type of patient. The left side one is the severance hospitals have heavy particle therapy. When the size is big and the depth is 11 centimeters deep, the amount of beam is almost same. When the depth is deeper, then radiation exposure to the surrounding tissues will be expanded. So depending on the situation, sometimes you need to use proton therapy or sometimes you need to use heavy particle therapy. So you need to look at the RB, relative biological effectiveness. If the normal tissues exposure is the same, then heavy particle therapy is better. But the right side shows the proton therapy statistics. So by using liver cancer cell lines, and we measure the relative biological effectiveness, depending on the genetic nature, the reaction and the outcomes varied. So individual variation need to be taken into consideration. So you need to consider the radiation sensitivity of the surrounding normal tissues. So based on that, you need to apply proton therapy or heavy particle therapy. And also there's a pros of heavy particle therapy. When the cancer cells are located in non-oxygen conditions, it's very hard to treat the cancer. But when it comes to the heavy particle therapy, is proven to be very effective in the low oxygen cancer. It is very promising treatment for low oxygen cancer. So here there's a small cancer cell, but after the application of proton therapy, it disappeared. For pancreatic cancer, so there's no progress survival for 3 years after the proton therapy. And when it comes to hepatocellular carcinoma, the proton therapy was really excellent. So the effect was the same as the liversectomy. So this patient has still survived for 6 years after the treatment. This is the intrahepatic carcinoma. People say that only surgery is the answer, but proton therapy was also effective in that type of patient. So you might think the proton therapy emerged all of a sudden nowadays, but that's not the case. The particle therapy or proton therapy history dates back to 1930s. So the first proton therapy happened at Berkeley Lab in 1954. And the ion therapy was introduced. And the big turning point happened when Loma Linda Hospital adopted proton therapy center at a hospital level. And in Japan, the heavy particle centrifuge was established at a hospital in Japan. And the first hospital heavy particle therapy equipment was introduced into Korea in 1986. That's when I entered the College of Medicine. So particle therapy was introduced in Korea for the first time. And this is the news coverage about that. It also features the prices of the therapy. And Dr. Chu made a proposal that Korea needs proton therapy. This new media coverage happened in 1995. So thanks to his support, in 2001, we were able to establish a relevant center. So the first therapy first proton therapy happened domestically in 2007. So Samsung Medical Center prepared for proton therapy. So finally, in 2022, we saw the accumulated number of patients reaching 5,000 who received the proton therapy. So it's quite promising, and it is increasing right now. So this is the statistics on radiotherapy in Big 5 Korean major hospitals. The red color refers to my hospital, Samsung Medical Center. So about 15% of NCC Korea received the proton therapy. And Samsung Medical Center, about 10% of patients receive radiotherapy. Blue one is the conventional therapy, and green one shows the modern radiotherapy. So I think in modern years, we have seen huge progress in radiotherapy. In 2010, the radiotherapy is reimbursed by the National Health Insurance for solid cancers. And this is the prospect. So indications might change depending on the coverage of National Health Insurance. So prostatic cancer, liver cancer, head and neck cancer, and upper gastric cancer. So these are the types of cancers which are covered by National Health Insurance for radiotherapy. So this shows the reimbursement for cancer type. So when it comes to head and neck cancer, we actually apply radiotherapy, the proton therapy, and about 20% of proton therapy is applied to liver cancer. So since the launch of our proton therapy center, you can see the increase of patients receiving proton therapy. G means gantry. It shows the number of treatment rooms. So we have 2 treatment rooms at Samsung Medical Center. So we have accumulated the patients receiving proton therapy with these 2 treatment rooms. When you look at the HERA statistics, so proton therapy is not covered by insurance. So proton therapy represents 3% of radiotherapy in Korea. In America, prostatic cancer took up the biggest part in proton therapy, but breast cancer is picking up, is increasing when it comes to the application of proton therapy. The proton therapy facilities are increasing a lot, as you see in this pie charts. So many countries see an increase in the application of proton therapy. So Samsung Medical Center has the rotating treatment facility, even though it was not launched yet. So within this year, this rotating type treatment facility will start its operation. This is the statistics in Japan. For a long time, carbon ion therapy was applied for these indications. Sometimes proton therapy is good, sometimes heavy ion or heavy particle therapy is good. So when you look at the recent reports, PBT and CIRT are comparable when it comes to side effects and efficacy. But there should be more systematic research required to compare these 2 types of therapies. Nurses and administration staff, we actually conduct a survey. So what was the biggest milestone at Samsung Medical Center? That was the question in the survey, and they said the establishment of proton therapy center. That was the biggest event at Samsung Medical Center, they answered. So many people want to receive proton therapy, but in order to expand the application, we need to have a proper reimbursement policy. So there are many patients wanting to receive the proton therapy, but we only have 2 rooms. So we are doing our best to apply the best proton therapy for the best efficacy. So at least 1 proton therapy center is needed per region. So proton therapy can only cover 10% of radiotherapy patients, and we don't have room to receive patients from other hospitals. So nationwide, we need to establish more proton therapy centers across the country. So the equipment is becoming smaller, and for heavy particle therapy, there's a rotating type equipment. I think it will be a great milestone. And dimension is also becoming smaller, so we will also reduce cost as well. So there are a lot of good prospects of proton therapy. In conclusion, we have really good prospects of proton therapy in Korea. As a non-invasive local modality, the local control probability of particle therapy seems similar to surgery. So for older patients, I think there's a great potential for particle therapy and proton therapy. And also, I hope there should be reasonable facilities and centers across the country for better application of proton therapy. Thank you.
Thank you very much. Let's hope the benefits of proton therapy we learned through these therapies and case examples will save more patients in a less invasive way. So let's give Director Park another big round of applause. And last but not least, we will proceed to the sixth presentation of this forum. Dr. Woo Jin-hyung, Professor of Surgery at Yonsei University College of Medicine, will deliver the presentation on navigation-guided robotic surgery. Professor Hyung serves as the director of the Gastric Center at Yonsei Cancer Center and is the founder and CEO of Hutom. He pioneered the development of a surgery navigation and analysis platform using surgery data science and AI technology. Notably, he holds the record for the highest number of robot-guided gastric surgeries in the world. After performing the first robotic surgery on a stomach cancer in 2005, a stomach cancer patient that is, as of 2023, Professor Hyung has achieved a groundbreaking milestone by successfully completing over 2,000 cases of robotic surgery for stomach cancer, marking the first time in the world. And Professor Hyung is truly dedicated to achieving more precise and sophisticated surgeries by integrating his clinical experiences with intensive research for technological advancement. So, ladies and gentlemen, let's welcome him with a big hand.
Good afternoon. I'm Woo Jin-hyung from the Yonsei University College of Medicine. The session is being very delayed, so let me try to make it very simple. Professor Hitar Park, the previous speaker, was my colleague at school, and he made his presentation short in courtesy of my presentation, so let me try to do the same for you as well. I'm going to talk about something related to a product that was developed in my company, Hutom. Today, I'm going to talk about surgery in cancer treatment. Gastric cancer, in around the 80s, first experienced surgery in Australia. So it was an open heart surgery. The traditional way has been used for a long time, and from the 90s, laparoscopy was started to be used. As you can see, the physicians would look at the camera, the monitor, and go through a hole in the abdomen of a patient. And a more advanced method would be robotic surgery, and my hospital started using this from the 2000s. So until recently, the focus was being minimally invasive with your surgery to secure the wanted outcome. That was the trend until recently. But when you look at the trend of the recent several years, especially after the match of Go between Isidore and AlphaGo, the use of AI has become very widespread also in the medical sector. So that triggered the shift between a hardware-focused surgery to software-focused surgery. So for gastric cancer, when we talk about surgery, you must be dexterous. It uses your hands. So those were the analog methods. But now there's been a digital transformation with surgery as well, meaning that more information is being used and the importance of knowledge has been rising for surgery. Surgeons say that surgeons learned how to operate on patients like a disciple, but there has been limitations. So overcoming this constraint has been an important issue. Until now, development of hardware was translated to better surgery. The better visuals you get, the better outcome of the surgery would be. And we thought the development of hardware would narrow the gap between two different surgeons, but there was always the gap caused by experience and knowledge. But recently, the software or knowledge-led innovation has brought about a big change. So no matter who you are, even without the same level of experience, anyone can be equipped with more knowledge. And you will be able to reach a better outcome, even with less experience. Sorry. The gap among surgeons will be narrowed down with a shift, and in the future, that is not so distant, any surgeon will show the same level of outcome, which would be most beneficial for the patients. So how would this be possible? As Professor Park shared, you saw many different images where we used technology to diagnose a disease and finding the target. And the image carries a lot of information, and how we use the information leads us to securing more information for operations. This has caused a lot of development in surgeries. The knowledge that we could not reach in the past is now securable, leading to better outcomes. Here you can see bleeding that has been stopped easily. So I've operated on 7,000 cases, and I think this is a very well done surgery because you don't see much bleeding. And here there's one vessel, so I thought this is the target. But as I operated, I found a severed vessel. So I had to find it again, and I would tie them up to prevent hemorrhage. So even after 7,000 operation experiences, these types of issues happen. We want to know the anatomical structure of patients before an operation, but the anatomy of patients are all different, even between twins. This means that we cannot generalize the anatomy of patients. 10 years ago, I used CT images in various ways to see if we can identify the vessel structures, and it turned out the images were very helpful. But these images cannot be understood by any ordinary men. This is an easy picture to understand for people who have majored in this sector, but as surgeons, we have to learn more information to be able to interpret the meaning of the images. So for surgeons, it's not easy to use these images on a daily basis. So to overcome this constraint, I used 3D printing. I wanted to reproduce the structure of the organ, and this took me more than 1 week. And all the organs are separately produced, so I cannot integrate them. So I changed my method, and I wanted to see if we could simulate surgery with 3D printing. It is possible, but very uncomfortable, and the structure is not exactly the same with the anatomy. So I thought this is not the way, and we need something that's more agile and real time. So I reviewed various ways, and there is the camera in the abdomen, and it helps us predict the location of the operation before the operation. So if we can create the virtual environment with an image, we will be able to understand the anatomy of the patient. And it should be friendly for the surgeon, and it should be very fast. And AI can be of aid recently, when you look at Sora, it's able to generate videos. So AI was very helpful in reducing the time required to create a CD image and visualize the resultant video. And you take a picture, a CT scan of the artery and the veins at a different point in time. And people breathe, and matching these two images into one is not easy. Another issue is to be able to easily visualize the location of the operation. So our first idea was, well, depending on the camera position, the angle where you can see differs. During the operation, there's the target that you want, and the virtual image must be able to be consistent with the actual location, which is not easy. And the level of pneumoperitoneum model is different based on patient. And the second issue is being able to create a 3D image in a short amount of time. And the third issue is, well, can you click on the video so it can be played on the right? So it's much more easier to understand now. This image is different from the atlas, but here you can see an image similar to what you see during the surgery, which makes the surgeon understand the situation more easily, and you can reach the location. Now, as I've mentioned, we can use a GPS system, just like a navigation system on your car during operation. And this product was developed by the company Hutom that I founded. So we have the pneumoperitoneum model that is patient-specific, and a matching model between the vein and the artery image, and a solution that creates 3D videos from 2D images. All of these functions were integrated in one system. So pre-operation, you can understand the full anatomies of a patient. So here, you have the pneumoperitoneum model, and you can see the anatomical structure of the patient, and instruments must be placed in the abdomen. But with this system, you can do a practice on the patient that you're going to operate on tomorrow, and you can identify the exact location where the instruments must be placed at. If you make a mistake, the instruments may clash, preventing inappropriate surgery. So can we use this during operation? So we can see two different images during operation and also study the anatomy pre-operation using a virtual model. So no matter how much level of experience you have, you can operate on a patient with the same level of anatomical knowledge. In addition, with one click, you can easily generate images of the location that you want. For example, in this hall, the right wall is lighted. And on my model, if you click with your mouse just once, you can approach the wall closer. So during the operation, you can confirm the locations that you want readily. So with one click, you can approach the side that you want. And in some cases, you want to look at the anterior and posterior. You must be able to rotate the image and get the image that you want. So the 3D model will be objectified and you should be able to rotate it during operation, and that is supported in our solution. So before operation, you can practice surgery and click on this area and you can go closer to the vessel and confirm the location that you want to see. So I'm going to later on show you what happens if you also apply AI here. So the location that you want to see can be confirmed with a 3D model. And during operation, this implies a lot for us. Well, the process is quite simple. You get a CT scan, and gastric cancer patients all undergo the CT scan. The scanned image is uploaded onto cloud to generate a 3D model, and based on the patient data, we come up with a pneumoperitoneum model, which is sent to the hospital, and this enables the surgeon to do a practice 1 day prior to the operation or use this during operation. So this is a practice. You can see each vessel beforehand. Usually 7 to 8 thick vessels must be ligated during the operation. And here for this patient, this vessel is very important. It leads to the liver. And this situation is unusual. So for this patient, this vessel has branched and you cannot be sure whether this has to be cut. And if you look closer, the two vessels are linked. And it shows that the blood will be supplied and you can resect the vessel going to the liver. So this is the actual video of the operation. You just saw that same vessel going to the liver. So you can resect each of the vessels. So it was very easy to locate this vessel because it was in the spleen, and you want to go to the right side and you want to look at the vein first, and you need to resect these two veins, and you've already seen this during practice, so it's much easier to operate on the actual patient. So until now, we did not have any option to confirm the anatomical structure pre-operation. Here you can see two different vessels and their position. So no matter who you are and what level of experience you have, the same anatomical knowledge is already secured. So the software that I developed now supports all physicians and surgeons. After the ligation, here on the right, you can see the gastric vein, and it's easy to locate this vessel. It was behind the artery, and you cannot miss it because we already have the 3D model. If you miss this artery, there could be a lot of hemorrhage. And to confirm whether we can really resect this vessel, we used angiography and tied this vessel hard, and the blood supply is signaled with the green, and you can see that it's expressed green still. So this type of angiographic procedure is not needed nowadays because you now have the 3D model. What's better is that we can be assured that you will be able to safely resect this vessel for the patient. This is another patient with the same vessel going toward the liver. But with this patient, it's different because there's only one vessel, so you cannot resect this one. And you can understand that there are 3 vessels leading toward the gastric artery. So in the past, we could not recognize this, no matter the level of experience that you have. So if you're able to identify the small vessels beforehand, each and every one of them, it's very convenient, and this is now enabled thanks to my software. So all of the vessels that we wanted to locate, the system located without any error. And you can go even deeper. Very specific information can be confirmed. And the result was that the operation time was cut by 10%. I never imagined that one day I could operate during a smaller amount of time. I carry out 2,000 robotic surgery, but even with robots, operation time does not decrease. But the fact that the system overcomes your knowledge level limitation enables us to cut the operation time. Console time here means the time I spent to operate on the robot console, and that time has been cut. This is for renal cancer. For the kidney, you need to be able to separate the cancer location with the spot where the urine is generated. And you need to be able to preserve as much kidney function as possible. And the location of the cancer cell must be located exactly, unless otherwise it would be hard to carry out a surgeon. So we're carrying out the development to come up with a model for kidney cancer and also for the lung. The less you resect for lung, the better outcome you get. And usually you inject gas during operation for your intestines, but with lung it's impossible. Rather, you need to be able to contract the size of the lung. And the situation is different depending on whether you're a smoker, whether you're healthy, and these elements must be predicted so we can place the instruments on the right location and come up with the right calculation for the outcome. So we're developing a model enabling a practice of lung cancer surgery. All of the physical properties are reflected. For gastric cancer, we already have the prototype, and we have confirmed the effects during a clinical study. We're currently writing the report. So as mentioned, you can practice on the patient on the previous day. So we used to say you only get one chance to operate on one patient. But that is no longer. You can practice 10 times, 20 times. And with the development of AI, we now have computer vision. So here you can see the organs, movement of the instruments, and what type of tools can be used during operation. And you can also understand the stage during the operation. So with this video, we can carry out analysis, such as whether there's hemorrhage, what stage they're at, with what type of tool, on what types of organs in real time. This is the navigation software that we developed. You don't have to manipulate or control the navigation system. It automatically moves to the position that you want and overlaps the actual video with AI-generated image. So automatic navigation is enabled. This version will be launched this fall, and the version on the right at the end of this year. So when surgeons operate, we could minimize mistakes that occur due to the lack of understanding on the anatomy. If this is possible, this will enable a patient-oriented environment on the operation table, the experience of the surgeon, and level of knowledge will no longer be a constraint. New technology and solutions, digital technologies will enable this further. In the end, the recovery of the patient will be facilitated and we can become better surgeons. Thank you.
Thank you for that interesting presentation with AI and robots, the keywords of almost all industries today. We look forward to this technology to immensely help with meticulous surgeries. So let's give Professor Hyung another big round of applause. And that wraps up Forum 3. Thank you very much for the excellent presentations. I would also like to thank all of our participants and distinguished guests for being with us until the very end. And before we leave, I would like to ask you that the QR code that will be displayed on the screen, you can participate in the satisfaction survey for this event. And please note that until March 22nd, we are conducting a satisfaction survey reward event. So we invite your keen interest and active participation to contribute to creating a world without barriers in healthcare. Once again, thank you everyone for joining us, both physically and also those online. And starting at 2 p.m. here in this room 401, we are going to start with Forum 4, the paradigm shift in the global healthcare market brought by digital technologies. So I hope for those of you attending Forum 4, I will see you again. And if this was the last forum you're attending, you might want to go online to attend the fourth forum as well. And for now, I'm going to say goodbye. Thank you very much.